Hi everyone, our topic for today is all about soil physical properties, such as the soil color and the soil texture. There are other physical properties of the soil aside from those two, but those other physical properties will be discussed on my next videos. So let's begin. The physical properties of the soil are often the most important properties for evaluating the suitability of a soil for a particular purpose. These physical properties can answer these questions. Can the soil support trees? Is the soil too anaerobic? Can the soil withstand vehicle traffic? And the answers for these questions will depend on the soil's physical properties. When you say physical properties, it refers to the characteristics, processes, or reactions of a soil that are caused by physical forces and that can be described by or expressed in physical terms or equations. These include the soil color, texture, structure, bog density, and particle density, porosity, water holding capacity, and consistency. So for this time, let us first discuss the soil color. Soil color reflects an integration of the chemical, biological, and physical transformations and translocations that have occurred within a soil. And there are three major factors that can influence the soil colors. And these are first the organic matter content, and we also have the water content, and the presence and oxidation states of iron and manganese oxides. So for organic matter, organic coatings tend to darken and mask the brighter colors of the minerals, meaning the higher the organic matter of the soil, the darker it is. In terms of water content, soils are generally darker when wet than when dry. And this water content also influences the oxygen level of the soil and thereby the rate of organic matter accumulation, which darkens the soil. It also affects the oxidation state of iron and manganese, and that will of course affect the soil color. For the presence and oxidation states of iron and manganese oxides, these two, or the oxidation states, or oxidation or reduction states, tend to give the soil the red, orange, yellow, gray, and bluish gray color. There are also other minerals that sometimes give the soil distinctive colors, such as manganese oxide can give the color black, the soil the color black, the glauconite, which gives the soil green color. We also have calcite and soluble salts, which can give the soil a whitish color. Soil color is a property that gives important information about the soil characteristics, and it is determined by comparing the color of the soil to the chips in the Mansell color charts. In Mansell color charts, soil color is consisting of three parts, which are the hue, the value, and the chroma. So this picture is an example of the Mansa color charts. In using the chart, what you can do is to compare the color of the soil to each chip from the chart. So each chip is or has a label for the U value or chroma. For example, in this one, for the U, which refers to the redness or the yellowness of the color, it is under the U of 7.5 YR, for example. No? Please look at the circled chip that is included on or has the same color with the one that is encircled in the Manser color chart. So for the U, we have the 7.5 YR. By the way, the U can be found on the right side of the chart. That 7.5 YR and that 10 YR. For the value, which refers to the darkness or lightness of the color, so it means that a value of 0 is equal to black. So for this example, just like on the first one, so the encircled example, we have the numerator of 5 for the value. And for the denominator, which is the chroma, which refers to the intensity or brightness of the color, meaning a chroma of 0 could be equal to neutral gray. So in this example, we have 8 as the denominator. So for complete notation, we have 7.5 YR 5 over 8 for the Mansa color notation. So as what I've said earlier, value is expressed as the numerator of the fraction. Chroma is the denominator. Low chromas have dull colors, and high chromas have bright colors. Another example is that, for example, we have 10YR3 over 2. So this means that the U is 10YR, the value is 3, and the chroma is 2. So the significance of soil color relates to the properties we can infer from certain colors. So for example, in the soil profile, let's begin at the top or at the surface. So this soil has a dark surface color, which has a Manser color notation of 10YR3 over 2. So below this layer is the 10YR3 over 3 color. So in terms of let's say organic matter level, because of the differences of in color of the two layers, the first layer or the surface soil means that it has a higher organic matter content than the second layer because it has a darker color. So for the subsoil that is 10YR4 over 4, it means it has a typical brown color. The 7.5YR4 over 3 is similar but redder. And the parent material is 10YR5 over 6. So that is how the soil color is being recorded. So the color of surface horizons reflects a strong imprint of biological processes happening in the soil, particularly those that influences the origin of the soil organic matter. So organic matter imparts a dark brown to black color to soil, and generally the higher the organic matter content, the darker the soil is. You can also observe mottles in the soil, just like in this figure. So mottles may occur either as splotches of reddish brown color in a gray matrix, so just like on this photo, or a gray spot in a brown matrix. It is usually the result of alternating periods of reduction and oxidation caused by seasonally fluctuating water tables. So it has something to do with the oxidation states of iron and manganese. So here are some examples of soil color and the characteristics or attributes it indicates in the soil. So let's discuss one by one. From brown to black, surface horizon, it indicates accumulation of organic matter. So as what I've mentioned earlier, organic coatings tend to mask out or darken the soil color. For a black subsoil, it indicates accumulation of manganese and or the parent material could be basalt. If the soil has a yellowish to reddish color rather, meaning it has a high content of iron in ferric form, which also means that it is a well-aerated soil, meaning the iron is present in its oxidized state. So there is the presence of oxygen. Another is we have gray or bluish green. It means the soil is high in iron in ferrous form, meaning the iron is in its reduction state, meaning the soil could be submerged in water for a long time, meaning the soil could be poorly drained. And another is if we have white to gray soils, it indicates accumulation of salts and or the parent materials could be marl or quartz. So that's it for the soil color. Now we are moving with another soil physical properties, which is the soil texture. So when investigating soil on a site, the texture of soil horizons is often the first and the most important property to determine. It will provide information about the following: the water flow potential, the water holding capacity, the fertility potential, and the suitability for many urban uses like the bearing capacity. So when you say soil texture, what does it mean? So soil texture, it refers to the percentage of the sand, the silt, and clay particles in a soil sample. So this property of the soil is critical for understanding the soil behavior and management. So this property of the soil is not subject to change in the field, but can be changed in potting mixes. For example, you mix sand and clay, or you mix higher amount of sand with just a minimal amount of clay, or you're actually um, making your own soil texture on a pot. But in the field, it is very impossible to change the soil texture. So in terms of particle size diameter or particle diameter size, it ranges over several orders of magnitude such as 1 meter for boulders, more than 2 millimeter for coarse fragments, less than 2 millimeters to 0.05 millimeters for sand, less than 0.05 millimeters to 0.002 millimeters for silt, and less than 0.002 millimeters for clay. So this particle diameters could be measured or could be separated by using the soil sieve, which has different sieve sizes or diameter sizes. Coarse fragment includes materials which are more than 2 millimeters in size, such as the gravels, the cobbles, the boulders. Actually, these are not considered part of the fine earth fraction. Soil texture refers only to the fine earth fraction of the soil, such as the sand, the silt, and the clay. So let's discuss the fine earth fractions. Let's begin with the sand. Sand are those particles having a size ranging from less than 2 to more than 0.05 millimeters. These particles are visible without a microscope. But if you view, but if you look at the sand particles using a microscope, you will see this one, just like in this figure or in this photo. This is what sand looks like when you view it using a microscope. So it has a rounded or angular shape. So sand grains usually quartz if sand looks white, or many minerals if sand looks brown. So as what you can see in this photo, you have those grains that are white and those grains that looks brown, meaning there are quartz minerals. The white ones are quartz minerals, while the other minerals could be composed of different kinds of minerals, such as those brown, black, orange colors. Some sands in the soil will be brown, yellow, or red because of the iron and or aluminum oxide coatings. So in terms of feel, so when you feel sand by using your hands, sand particles feels gritty and considered non-cohesive. When you say non-cohesive, it does not stick together in a mass unless it is very wet. So sand particles have low specific surface area and has less nutrients for plants than the smaller particles. The voids between the sand particles promote free drainage and entry of air. And because of the large voids, sandy soils hold little water and are prone to drought. So next we have is the silt. Silt are those particles ranging from less than 0.05 millimeters to greater than 0.002 millimeters. These particles are not visible without a microscope, but when you view silt under the microscope, you can see this sample photo. So that is silt under the microscope. So quartz is often the dominant mineral in silt since the other minerals have weathered away. So in terms of feel, by using your palm, your hand, silt particles does not feel gritty and have floury feel or powdery feel. So wet silt does not exhibit stickiness or plasticity. The smaller size of silt allows rapid weathering of non-quartz minerals. Since silt has smaller particles, it tends to retain more water for plants and have slower drainage than sand. Silt particles hold more plant nutrients also, but however, it could be easily washed away by flowing water and it is highly erosive, just like what happened in this figure. And the last fine earth fraction is the clay. Clay are those particles having a size of less than 0.002 millimeters. It can be viewed as flat plates or tiny flakes under the microscope. So that photo is clay under the microscope. Small clay particles are called the colloids, and these particles, if suspended in water, will not settle and have a very large surface area. Meaning, in chemistry, when you review chemistry, if a material has a large surface area, it is highly reactive. So clay has something to do with the chemical reactions happening in the soil. So wet clay is very sticky and it's plastic, or it can be molded readily into a shape or a rod. Oh, that is a clay, not an animal manure. So clay can be easily formed into long ribbons. Clayey soils have the capacity for seasonal shrinking and swelling, depending on the kind of clay that is present. The clay pore spaces are very small, thus the movement of water and air are very slow. It has also high water holding capacity, and because of that, not all of the water is available for plants. And also, the shrinking and swelling of clays affect buildings, roads, and walls. And also, as what I've said earlier, because of its large surface area, the chemical adsorption is large. So this table shows the influence of soil particles on some properties and behavior of soils. For water holding capacity, sand has the lowest water holding capacity and the clay has the highest. For aeration, sand has a good aeration while clay has a poor aeration. In terms of drainage rate, sand has a high drainage rate while clay has a very slow drainage rate. For SOM level, for sand it is low. For silt and clay it is medium to high. In terms of the composition of OM, organic matter, in sand it is rapid, in clay it is slow. Among the property or behavior listed in here, silt is almost always in between the low or the high, the good or the poor, or the rapid to slow. Silt is always almost in between. Let's look at other properties or behavior. In terms of compaction, sand is low, silt is medium, clay is high. In terms of susceptibility to water erosion, the most erodible one is the silt. The lowest one is the sand, unless it is fine sand. And for clay, its susceptibility to water erosion is low if it is aggregated, but if it is not aggregated, meaning present in large clumps or clod, it is high. In terms of shrink swell potential, sand has a very low shrink swell potential. And that's what I expected. Clay has a moderate to very high shrink swell potential. In terms of sealing of ponds, dams, and landfills, both sand and silt has are poor, while clay is high. Other properties and behavior, we have suitability for tillage after rain. So just after the rain, it is okay to till the land or till the field in if the soil texture is sand. But do not till your field or your land when soil texture is silt and clay. It will lead to negative results such as compaction or your seeds. If you till your land for planting, maybe the seeds that you'll be sowing will not germinate because of compaction. In terms of pollutant leaching potential, because sand has a low water holding capacity, of course, it will have a high pollutant leaching potential compared to silt and clay. It has the highest ability to store plant nutrients. For sand, it is poor. For clay, it is high. In terms of resistance to pH change, for sand, it is low. For clay, it is high. So again, in these properties or behaviors, silt is almost always in the middle or in a moderate level or medium level. So this is the soil textural triangle, which contains the 12 kinds of soil textures. This soil textural triangle can be used to determine the soil texture once the data on the percentage of the clay, the silt, and the sand is known or are known. For example, the data on the percentage of clay, silt, and sand are given, which are 80, 10, and 10% respectively. So just by using a ruler, you just connect the lines from each respective soil separator soil particles, and you will arrive on the area where it intersects. Oh, put a dot on it, and on this example, we arrive on the clay, meaning the soil has a clay texture. So under the coarse textured soils, we have the sand and the loamy sands. So on the lower part of the triangle, you have the sands and the loamy sands. For moderately coarse textured soil, we have the sandy loam. Under the medium or loamy soils, coarse, medium textured soil, we have the very fine sandy loam, silt loam, and silt. Under the loamy, moderately fine textured soils, we have the sandy clay loam, silty clay loam, and clay loam. And for the last one, for the clayey soils or the fine textured soils, we have the sandy clay, the silty clay, and the clay. Located on the upper part of the soil textural triangle, rather. Oh, so that's it. That's all for now. In my next video, we will discuss the soil structure. Thank you very much for watching. Please don't forget to like and subscribe.